physicist and senior demonstrator in SMS Hospital, Jaipur, India. I am moderator for today's lecture. I welcome you all participants to third lecture of third e-learning program organized by SCM-PCR. Main objective of SCM-PCR is to organize awareness, prevention and screening program for cancer disease and also to provide adequate training to all personnel associated with cancer treatment. SCM-PCR will establish the clinical residency program for medical physicists in future. This is a good platform for teaching, learning, sharing knowledge between young medical physicists. Today topic of lecture is brachytherapy dose calculation, which is going to delivered by diploma engineer Renate Walter. She is medical physicist. She is medical physicist and radiation protection commissioner in General Hospital Augsburg, Germany. In 1998, Renate Walter finished his university degree in geophysics at Berg Academy, Freiburg Technical University of Mining and Technology. After a family time of 5 years with 3 children, she started at a correspondence course in medical physics at Technical University, Kaiserslautern, finishing with certificate in 2005. Since April 2007, she is working as medical physicist and radiation protection commissioner at General Hospital Augsburg, which is now University Hospital Augsburg. In 2010, she was certified by German Society of Medical Physics DGMP for field of radiation therapy. In 2008, the radiation oncology department started with a new equipped brachytherapy unit. Since then, she is in charge of this unit. From the beginning, she treated not only gynae case but also skin and anorectal and head and neck cases also. Because of her experience as clinical physicist in brachytherapy, she was invited to contribute working group for dosimetric norms and consistency test norms which are part of German system of standards. In 2018, she joined GAC-Astro Head and Neck and Skin Working Group, and 2019 she was invited to contribute GAC-Astro Brachytherapy Workshop and on the Astro Indoors Interdisciplinary Teaching Course on Head and Neck Brachytherapy. Her another strong professional interest in transferring knowledge on radiotherapy physics to low and middle income countries. Now I invite our speaker, diploma engineer Renate Walter, to deliver her talk. During the lecture, please, if you have any question and suggestions, please type in chat box. And I also request to all participants, please mute your microphone and turn off your cameras during the session. Now you can start your presentation, ma'am. The floor is yours. Please start.
Yeah, thank you very much. Hello and good afternoon, good evening, and maybe good morning, depending from where are you listening. Okay, now we are here. Sorry. Good. Okay. So first I want to thanks to the organizers for inviting me to contribute. And I want to acknowledge Dr. Frank Hensley because he submitted some slides to me. So in the beginning of my presentation, you will see slides coming from him. So they are very familiar to you. So there is a certain overlap between our two presentations. So I start with the slides from him, and then I will go on to my slides. And on my slides, you will see some nice calculations in the ACE algorithm, which is a collapsed cone algorithm for brachytherapy developed by Lecture. They supported us with a free loan of hard and software, so we could do some tests for this in the hope that we can buy it in the nearer future. And my hospital switched 2 years ago to a university institution. So we are now University Hospital Augsburg, and we are using brachy equipment from Electra. This is a microcellatron with an iridium 192 HDI source, and so maybe I'm a little bit biased by this because my whole experiences on this system. So I want to start with a look backwards. So already 92 years ago, there was a little book published on dosimetry for brachytherapy, and it was very interesting what was written there. So the physical measurement of the dose has so far been little worked on. The radium therapist helps himself by determining the time which leads to an erythema. So this is the erythema dose. Maybe you have already heard of it. And the dose at a distance of 1 centimeter from the center of the preparation is relative described as hundreds. So this is usually a way how to normalize the dose as we do it now, still nowadays somehow. Or you find these 1 centimeter later again. So, and in the same book, there had been shown some applicators. Those of you who had access to an old institute or working there with 50 years working tradition already, they may have seen such applicators. I had the luck to see them too. In another hospital, we do not have these nice old-fashioned applicators in our hospital. Yeah, so we are quite happy that we are not anymore in that time where the physician tried out to just by trial error find the dose of his of that what he had in his hand now. Okay, now you remember from yesterday, you have seen these nice slides from Frank. There is there are some significant differences between the dose measurement you have got for brachy and when you have that in mind from EBRT. Yeah, so you have here the field, and you're quite far away, and the little chamber here. While when you want to go very close to your source pellet, yeah, you have a strong dose decrease in a usual ionization chamber, and this is a very big problem, not only for this point of a calibration of your source, but when in the end we want to talk about new algorithms too, and there you have got the problem of in vivo dosimetry. So by now there are not very good recommendations developed how to do in vivo dosimetry or how to check your new algorithm. So yeah, so you remember that there is the reference air camera rate. Sorry, I have to or something else. Good. Yeah. And so you may remember from yesterday that we call connection of the individual source to the dose calculations. I see that now the slides are a little bit distorted and not like I prepared them, so I hope it will be getting better later. However, we call the connection of the individual source to the dose calculation the source specification. So the quality we use for the source specification is the reference air camera rate. And the reference air camera rate is measured in free air without any scatter contributions from the surroundings at a distance of 100 centimeter from the center of your source. So let's go on. Yeah. Okay. Let's see if this works. Okay, this is a little bit better. Can I hope you see still enough, and I have to see. Yeah. Okay. Now we see it better. Yeah. So you remember you have seen that slide 2 yesterday, and you see here the source. You see here the measurement, your measurement equipment, or usually this is done in the laboratory of the vendor, not at your clinic. And you need to know something for our algorithm. What is the dose here in water? Yeah, so here you are in air with your chamber, and here we want to have a dose rate or camera rate in water. So Yeah, and so we must have the air camera rate at the 1 meter distance. We want to know what we want to know is the absorbed dose to the, sorry? Was there a question in between? Okay. So we want, what we want is to know the dose, absorbed dose, and water in distance of a few centimeters. So it will be converted, the camera rate from 1 meter to the distance d, which is here in the algorithm 1 centimeter. So you can do this by the inverse square law. This actually shows why the dose specifications in air camera is quite practical. Yeah, so good. But what you already see here, this is the nice inverse square law, which comes up from something else. So let's take a look. Oh, yeah. Some changes happened here, which is not that nice. Okay. I have to provide you a PDF later that you can see the original, because I don't know what happened there. Okay, but what is important to know, I made here a little point, which is my source, and this is the encompassing surface surrounding the source, which is for a point source, which is radiation, homogeneous, giving its radiation in a homogeneous way. So the radiation is given away just equally for each segment of this, or for each surface surface part of this sorry of the sphere. Yeah, so what you should read here, I don't know, that the number of particles, or the fluence rate, is defined by the number of particles are going through the surface by time, which is equal activity divided by surface. Yeah, so, or activity, and the energy fluence rate is activity times energy divided by surface. Yeah, and the surface of a sphere is simply 4πr in the power of 2. So this is the origin of our inverse square law at that point. And you may know this from other, from your university times. These belongs for other physical laws too, that they change by the inverse square law, like, so gravity is dependent on this too. Okay, but so keep in mind, it has something to do with these, with this surface surrounding our source. So, okay, oops. Okay, I'm a little bit surprised by these nice slides. Okay. So, all right. I think I have to pass this much faster. I know that Dr. Franz Hensley has provided a lot of interesting notes to that, and I think I should try to go through this quickly, and we will provide a PDF if he agrees with his notes, which is more helpful than seeing not really what's written there. And I hope when I come to my slides, it will be improved a little. Okay, so we go through that. Yeah, so you see this strange side too. So I must apologize, I didn't realize that is changed in that way. Okay, whoops. What happened here? I don't know. But there is a little fun fact I would like to share. This is a slide on the CVAT.
Madam, it would be better if you share your screen.
Yeah, maybe I should share my screen. So let's see. Okay,
Yes.
let's
Just
try that.
open the presentation and
Yeah.
share your screen.
I have to open once again my, because it is not in the moment open. Okay, I go for this. Yeah, and okay, now I have to, so wait, okay. See how it works. Okay, I must now go through my own. Oh, so for my part, it's now working much better, but I'm missing something else. And I need something behind. Okay, good. Yeah, that's much better. Yeah. Sorry, I have to reorganize now my screens. I am using two screens. And I'm sharing one. No, not that. In one screen, and I want to have, want to see you too. And let's see how it works. And yeah, I think I can work like that. Just a moment, please. I'm sorry. Okay. Good. Okay, good. Right. So, yeah. Okay, this looks a little bit better. I hope I can work with this. So, yeah. Let me go back a little bit because we missed something on here. Okay, so we had this calculation, you remember from yesterday, and now we see it much better. What I wanted to make clear is that you have a perfect point source with an equal radiation in each direction, giving an energy fluence rate, giving an energy fluence rate, which is activity times energy divided by surface. So in my opinion, this is something very simple and basically, where you might wonder why I'm talking about this, but I realized that very experienced colleagues do not have this little point in your mind that this is because you described the spreading of your energy of this on the surface of the sphere, which is growing by the surface is growing by r by the power of 2. So okay, now we have this to get to the point source or to get the dose of the point source, we need the reference air camera rate, which is defined in 100 centimeter. You go back to your 1 centimeter. You have mass energy transfer coefficient, and you have a correction factor for scatter and absorption. In the past, it had been these Meissberger polynomials. Yeah, and some correction for Bremsstrahlung losses. Yeah. So this formula you saw before was made up for the perfect point source, but very early they started to implant iridium wires with certain lengths or other radioactive wires, maybe not iridium because it was not at that time available, I think. And so they needed, there was a need for another formula. So Sievert introduced this integral already 100 years ago. So you can celebrate this year, 100 years Sievert integral. And the solution of the Sievert integral is as well a numerical way. It's not analytical to do that. So you see, this is very difficult to use in in your daily work life. Fortunately, the task group 43 developed a formalism, which is quite well known as TG43, where it was reported. And this report, although for all who do not have access to the Medical Physics Journal, this protocol is free for download for everybody on the AAPM site. Yeah, so when you Google it, because it is a separate report, so it's available. I think Frank mentioned this yesterday too. So very important is to have the access or these addresses where you can get onto pages where you get the descriptions of the sources. Yeah, so we have here now, let's take a look on the detail of this algorithm. So you need the air camera strength. It is replacing the reference air camera rate. You need a dose rate constant, and you need a geometry function. And these inverse square law is absorbed in this geometry function. And
sorry, ma'am, for disturbance. We have limited time, so please try to complete your slide timely. Thank you.
Yeah, thank you that you remind me, because I lost some time in the beginning. Okay, you remind the coordination this time, which was shown by Frank yesterday too. So we go by this just to keep that in mind. All right. And you see here, I just picked up these curves. Important is, I know some of you may use, or I'm quite sure some of you are using cobalt 60, and the other group may use iridium 192. I do not know how much cesium 137 is still available. So for HDR brachytherapy, this is the main sources which are now available. And you see something here, there are some significant differences here. Okay, let's go on this. I think you have shown this. Good. Yeah, so I just paged through this because I think you heard it. And let's see. Good. Okay, now we are here. I'm sorry, there is not best. Okay. So from one of these nice sites you have seen, or you were, yeah, Frank mentioned, you can get the full description of your source. This is now the model of the MHDR source for the nucleotron microselectron machine. This source is built in our machine, or this specification. You see here a little image how it looks like in reality. So there you see it's not a point source, but it has a length of 3.6 millimeter. When you go to your planning system, you can adjust your normalization and add some nice isodoses that you can make it really visible. Yeah. So what you see here, the 9 gray isodose, shows me this palette form too. So our system knows that this is not a point source anymore, but it is a real little source palette of 3.6 millimeter. So when I'm working with only one dwell position, I am still in that point that I can say, okay, it is like these inverse square law is still kept. You see here my profile going along here, and I picked up 2 points here. So in a distance of 0.14 centimeter, we have almost 100 gray from the source. And when I go into the distance of approximately twice as much, I have only a quarter of my dose. So right in that direction, it's working quite fine, although I have here not enough dose, so it's a little bit the dose coming closer to my source. This is due to the shielding due to the encapsulation, which I have here, and here I have the cable. Yeah, so this is the tip of my sources in that direction, the cable in that direction. So when you take a look into 3D dose distribution, you see here it's looking almost like a sphere, but it's a little bit flattened up here and down here. So yeah, so this is for the single source. However, in your planning system, it is working in the background, and it is calculating for every source a certain weight, how much you need to get the dose at a certain point, and then sum it up. So let's take a look how it looks, the dose change gradient of a treatment plan by distance from developed position layout. Due to the growing encompassing surface, quite often doesn't follow in clinical the distance with the distance the inverse square law. So I remember that somebody yesterday asked at this, and it comes by that now your dose calculation or your planning system will give up, or you can adjust the isodoses there, that you have a more smooth one, but as far as when I look here, it looks not very optimized, but it is just like keeping equal times everywhere. And now it is not a point source, but it is something like comparable to a wire. And of course, when you are close to this, you cannot handle it like a point source, and it doesn't follow in its dose gradient, or the profile doesn't follow the inverse square law. So as an example, at almost 3 millimeter distance from the source, we have here 10 gray, and if we want to go to a quarter, or a quarter of this this dose, which is by around 2.5 gray, you need more distance than just double the distance. You see it? I hope so. And but the dose, when you go, it is a different if you are very close to your sources or if you go far away. So I prepared here an image for a dose profile. This dose is this is a profile of a line of 9-12 position calculated in non-center brachy, like for a vaginal calf treatment. And it was a little bit optimized here, as you can see. And the treatment is calculated for a 3 centimeter diameter vaginal calf applicator. So our distance to the next well position from our starting point of the profile is 1.5 centimeter. So when you look here, we are here at the point of 2 centimeter distance from the source. Yeah, so it is 0.5 centimeter from the beginning of our profile. So you have to add these 1.5 centimeter, makes 2 centimeter. And we are here with 5 gray. And when you are in a distance where you have only a quarter of it, you are at 4.75 around. Sorry, 4.75. And this is a little bit more than just the double distance. So it is depending where you are, and the more far away you are from your layout of your dwell positions, the more it gets to, the more your profile and your gradient goes to the inverse square. And this was now for only, what you have seen was only for one dose line layout. But when you go and have several catheters, like in that example. You see your 100% isodose, or the prescripted dose here. It looks like a pillow. And you see here a few profiles. And of course, when you take this pillow structure, you need a larger distance to come back to this inverse square law. It is very interesting to see this simple point that is very often forgotten. Yeah. So when you talk to your physicians, it happens very often that they say, okay, there is the inverse square law valid, and they forget that a layout of several catheters with a lot of dwell position doesn't lead to or is not in the close vicinity following the inverse square law. So here's another example, and it can be up to so like this. It is almost 6 times. I come down here, yeah, but you see that it's changing, yeah, a little bit. Good. And here again, you can have, I prepared to have these as an overlay. So for one sphere, which is loaded, you have this nice blue line, which is quite steep and following the inverse square law. Oops, sorry, where am I? And for 4 times by 4 times layout, you have this red line and the green line. So what is important to know, it is dependent on the hole size. Yeah, so the whole size of your implant, of your flap, the length of your esophagus applicator you have loaded, or if you have a long vaginal cuff treatment and so on. This changes all the steepness of your dose curve from your complete plan. So let's go on. So all this is done now or in water. So we have no consideration of any inhomogeneities. I have shown you a lot of examples in on the surface, because we do a lot of skin treatments, not only gynae. And in the past, we used some shieldings in gynae, which is not taken into account. And so for us, especially when you're working at the surface or on the surface with surface molds or with flaps, there is the missing and additional scatter of radiation. So of course, at least for those who are working with Iridium-192, we need better algorithms. And I think it's even for those or for them who are using the iodine seeds and working in a very low energy area, they need them even more. But I'm not sure if for iodine seeds the new algorithm are already available. But for Iridium-192, it is already available. So there are there are 3 ways to do this. One is the separation convolution algorithm called collapsed cone, or ACE algorithm. It's the name it got from the vendor. This is developed by Lecture. And so when I go on and you see some slides on this, they are all developed in, they are all made in this collapsed cone algorithm. The grid Boltzmann solver might be faster. If it's better, I cannot say, because I do not have any experience with this, but it is, you can get it from the vendor variant, and you can try to get some Monte Carlo calculations. I think there are 3 Monte Carlo machines available, but you have to be very experienced to go on with Monte Carlo. So you remember from these, I think Frank showed, you remember the slides Frank had already shown yesterday, I'm quite sure. And yeah, so very often you see this lower dose due to missing scatter, yeah. So, and it is very important to see what we are talking about, yeah. So if you are 1 centimeter away, you have an average, or you might have a dose difference of 1.4 centimeter, but in 5 centimeter, it is already 11.5, and it's getting larger the more far you go away. This seems to be a very strong mistake, or yeah, so coming from here and having a dose miscalculation of over 40%. But you will see that is not that important here. So let's get started here. And I calculated in a Fantone. You have seen this image. This is TG43. And so I defined some, I worked in an artificial, let's say an artificial data set. So you have in the Oncentra software the opportunity to give in an empty image series. You define the size of your image series, and then you can start to draw some contours in, and you can add to the contours some material and define material for the main contour and take water or adipositous or fat or muscle or else. Yeah. So here I defined some structures which are just only air-filled and surrounded by water somewhere in the body. It could be 2 adjacent parts of esophagus and bronchus, in example, which could be air-filled for a while. So when you now compare how it looks, here you had the TG43, and here you can now take a look to the TG186. So we are somewhere inside the body. We have a certain distance, so to the outer part. And you see the influence here on the lines, which look a little bit different here. And caused by some air inside here. And when you take a look here, in this ROI, we have air in too. So you see that my isodoses are pressed in that direction. Yeah. So, and when you take a look here, here's my airfield neighbor ROI, and here's my airfield main ROI where I have my source place, and here I have got water. Yeah. And so you see when you compare this side and this side, you see, okay, I have a little bit more dose there. And so when you just take these 2 points, so your 1 gray isodose is hit, that is the 1 gray isodose hits that point. But on the other point, comparison point, you have already a lower dose. Yeah, so in air. So this was inside my box, which is looking like a, yeah, in the size of the head. So I tried out what's going on when I place my my little flap, or place a little flap onto the surface. And I have chosen. So here you see my water or my external line. Here's air. Here's my body filled with water. Here I have another ROI constructed, and in the next slides you will see what happens when this ROI. Oops, where am I? When this ROI is filled by different material. Yeah. So this is the TG43 calculation, how it looks like, and you see here how it looks like in the depth somewhere here, and this is the image in the depth equal to this line. Yeah. So let's see what we can see here. Okay, and now in that cavity organ, the green line, I filled water. So what you see here is not caused by this water organ or additional water, but by the lack of the scatter. Yeah, so there's and you see, but you see still here it looks quite equal as that what you have seen before. So now take a look again. So now I place this two. This is the TG43. This is the TG186, but with water in the cavity. Now you can see that. So when we now go on and fill this cavity organ with air. Now here is not water inside, but air, and immediately you see here there is much less dose. Yeah, and so it goes on, and we can say, okay, let's take a look what might happen if we have something with a lung material. So this is the inflated lung. It's not only air, it's a little bit more than air. And you see an influence on that too. It is not that much dose as we found for water, but it is more than for air. And let's imagine it is not no air, but there is a cortical bone inside. It happens that we place flaps on extremities like legs, yeah, so it can be very close to bones. And we have a different view on this too. And you see all these points here, they were directly compared. And this is the result of this dose comparison. So I have the material water, air, lung, inflating cortical bone for my green contour. And this with the different mass densities. Yeah, so water was 1 and air is 0.001, and lung inflated, we have got this, and for cortical bone, it's almost twice as much as for water. So the mean deviation for all these points you have seen to the TG43 was, I show you here. So this means that when I compare the TG43 and say, okay, TG186, that is the right dose. So I find that my dose calculation is now almost 2.6% higher from TG43 than it is in, hopefully, reality. Yeah, so in TG186. Yeah, so when I have air, I have a larger air inside. I have a larger deviation. The inflated lung is not that, is a little bit higher than just filled with water. And when I have the cortical bone, I got a mean deviation which is smaller than water. So, but I compared these three fillings with the TG86 calculation with the water filling. Yeah, so I compared this with TG86 with this. So, and I got this slight deviations, which are quite small. So, and now these small deviations in the blue column, they belong to the difference in material inside this green organ at risk or structure I put there. And when you take it together, so if you add this and that, you come almost along to that point. Yeah, so it is like a separation of your scatter and your, or you see the difference between this, just the scatter and the material caused deviations. Yeah, so you have 2.6% caused by the scatter, and this is what is caused by the material. Okay, so maybe you have heard that people say, okay, there is a certain lack of scatter when I do skin treatments. And so maybe I should place a water bag on on my patient or on this flap. You have to be very careful, because when you use 6F catheter and your water bag is placed on the catheters outside from your flap material, you can press onto the water bags and so cause some changes in the positioning of a ½ millimeter of your source inside. So, however, I did a calculation, so just the theoretical part. So this is the TG43, and here you have the TG186. And you can see here, down here we have water, and we are and this is our flap made of Zelastic. This is the material which is used by Elector, and this is defined as a water bag. So here we have just density 1 for both cases. And so you see here some changes in the form of your isodoses here, and which are not, you don't find here. And the second idea I have already heard. So you remember that we were talking very strongly about the point of this gradient or the dose profile. And I have shown you the dose profiles of flaps. So I know of colleagues, and it's already published, some say, okay, let's take more material between our flap and the skin to be in an area of a less steep dose gradient. Yeah, so I did a calculation, another calculation of your here, and placed here some water or material equal to water, and I placed here something like Zelastic. So this was how it was defined. And again, here we have water down here. You can see it here too. And I did the two calculations, and you see some changes here too. And so the results of these two experimental calculations had been now this. So the mean deviation to the TG43, when I have the flap on skin but not covered, so I have almost 2.6%. When I put a cover of flap, 1 centimeter water thickness, I have only a deviation that my TG43 is calculating 0.8% higher dose than I can expect there really. And when I add 1 centimeter water equivalent, but no additional cover, I have even more deviation. And this is because I'm more far away from my source position, because I have to go into so I have to reach the 3 millimeter tissue depth in the skin. So, but my my distance between my dose points or my area I want to treat is getting larger to the sources. So the scatter factor plays a larger role, and yeah, so you need an additional calculation to check out how much you need to correct that scatter or the miss of scatter here. So, and then I was wondering, somebody was telling in the talk yesterday or asking for this, that they use a contrast agent for better delineation. I just picked out a test case from a lecture. This is not a case from our
Sorry,
hospital.
ma'am, for disturbance. Only 10 minutes has left.
Yeah.
Please try to complete your slides timely.
Yeah. So the delineation of target and organ at risk for gynae. In my experience, it is that we can very good see in our CT scans the bladder. So therefore, I was surprised that you need contrast agents. So, but I saw on that test data set, there, depending on the material you use for catheter, for bladder catheter, what else, it makes difficult to delineate the bladder. So anyway, I tried to set up a case to come to your question. So here you see something like a bladder inside a box. Yeah, it's only, oops, sorry. it's only a box. Here you have got the vaginal applicator, and here you have a structure which I would call rectum. So bladder, applicator, rectum. And I placed my points around there. So, and I tried out again different fillings. So this is a TG43. You see nothing. You see what you are used to know. And now I did some calculations. This is filled with air, and this was filled in the first with water density. So I changed in that green region. It was always air because rectum is very often filled with air. And here I changed from calculation to calculation the filling, and you see then the density. Yeah. So when it's filled only with something like water, like urine, it's not that big problem. It looks quite equal, but I was because I didn't knew how dense this contrast agent actually is. I just try out some higher densities. This is the density now of cortical bone, which is twice as much as for the water. See here. So, but it doesn't make so much difference to the other. Yeah, so I go back once again with water. You are very close. You are inside now here. And it's not moved very much. But I found another material. I do not know what it is really, but it has a density 8. Yeah, so a gram per cubic millimeter. Sorry, cubic centimeter. And when there is something inside of which is very heavy, so it would cause that by the scatter from that you have here much more dose. Yeah. So therefore, it would be best that that very person who asked yesterday what is going on in the bladder of the patient, please be so kind and write to me or to the organizers that they proceed your mail. Please write what are the specific agent, contrast agent you use, or what is the real density. So because when I see this, in case it's really heavy, well, you have a much higher dose for the bladder wall here. Yeah, good. And but what is very important to keep in mind, these are calculations only for iridium 192. So this behavior depends on the energy and the energy spectra of your source. And you know, cobalt is in a totally different energy region. So you cannot say, okay, I saw some interesting slides and here was so much dose. And when you work with cobalt 60, this is not the truth for cobalt, okay? So let's take a look on the comparison of these now. So I changed for the density for the bladder, and I had left from my applicator in the tissue a data a point set. I had in the tissue between applicator and my green structure, which I called rectum. I had a point set in the rectum, a point set which was beyond the rectum, and I had the point set inside the bladder, and I had a point set beyond the bladder. So, and when I fill the bladder with water equivalent, so yeah, I have from the TG43 is just due to some air inside the rectum, calculating for the left side a higher dose than there is really there, and the dose calculated for the area between, or for the tissue between applicator and rectum is higher. So now here we see a very high deviation, yeah, but this is inside the rectum in air, and this is not the calculated for tissue, yeah. So points in air have a strong deviation, but this is not of clinical relevance, yeah. So And when you see now the tissue beyond the rectum is underestimated now. Yeah, so the dose is higher than calculated by TG43. But the side effects, they come from the area which is between, is more here, which is between the applicator and the rectum. Yeah, so this is not of that is clinical almost meaningless. Yeah, and the same is when you go beyond. So when you go inside the bladder and the points in that area where the liquid should be, so it doesn't play a role. Yeah, so even if this is a contrast agent of a high density, who knows? Yeah, because it shouldn't be there in a couple of days anymore. Yeah. So when you go beyond the bladder and there's only water, you have an overestimation, which is here clinical meaningless too. You know, always, and here again, you have a dose overestimation by the TG43, because in case it is something dense in it, like bone, of course you have less dose there, and the TG43 cannot, and especially for that high dense material. Yeah, but it is these points with this wrong dose estimation, they are not of clinical relevance. Yeah, this is what you have to keep in mind. Okay, and yeah, so okay, so this leads me to okay, 2 minutes are left. So if we do we really need these new algorithms? If we can we see impact, or which benefit can be impact? And so when you go through the literature, I go quick through this, you see very often there are very low deviations in the area where you need the dose. Yeah, so the results for the cervix, and even in the what was publicated, that what was published. Sorry, very often you come to there are conclusions written down. Yeah, we need some more investigations on this. There's another nice paper in the medical physics, and you see here quite nice the red zones of the greatest deviation. They're usually quite far away for your treatment volume. So overall, very often you overestimate in the regions where you do not want to treat the dose. Okay, so I think sorry, and so we come to the conclusion that for gynae, there's almost no real evidence that you have some that there is some dosimetric impact in the literature to be found, and I do not expect that. And maybe for breast, and so I come to my summary. Oh, sorry, what is going on here? Sorry, and so overall, the TG43 provides a basic calculation formalism used in present treatment planning. So the data is available on the internet. You have seen these slides from Frank Hensley, and they take care to have the actual Excel sheets there for the data. And the formalism is applicable for commercial high and low energy sources. So it should be there for every planning system now. But it has this limitation. The calculation is in an infinite water medium. Although there is no consideration of inhomogeneities for the clinical use of iridium 192 and maybe cobalt, and I assume so for cobalt 62. It is not that important to have to consider the inhomogeneities when you are working in this in gynae or in gynae and in prostate. Yeah. For shielding, you have usually an overestimation of the dose. Beyond the shields, your shields at the side of the shields, there could be some more scatter dose, but your shields are not directly to the skin or to the tissue. There is always usually some of your applicator around them. So especially for those who are working at head and neck and skin, there is most probably or we can expect a little significant lack of scatter radiation, which is missing, which is reducing our real dose, so that we do not treat at that dose we expected as usually a lower dose. What's not clear is how we have a backscatter from jaw bones when we do tongue ground. So maybe we get there a higher dose. This is not investigated yet. So, you have material dependence of dose from low energy sources, and that can cause errors. And the new algorithms for Iridium-192, they are available and expensive, but they have the FDA and CE certification. So thank you for your attention.
Thank you very much, ma'am, for your informative and excellent talk. And thanks to all participants for interest in this program. There is one question from participant Ghulam Abu Zakaria sir and Professor Dr. Thank you very much, ma'am, for your informative and excellent talk. And thanks to all participants for interest in this program. There is one question from participant from Deepak Kumar Jaha. What do you suggest to overcome for missing scatter while using TG43 for surface mold skull case?
Yeah, so well, one point is that very often, or the prescribed dose is, or the experience with the dose is made just with this TG43. So we in our clinic, we just use it as it is. But if you want, you can add some more material. I used here for my calculation something like 1 centimeter water bag. Yeah, so this is not too heavy for the patient. Maybe you have some molding material, but I do not know how much it gives, how much of the scatter is will be there with this molding material. So it depends on the material too. If you have something what is water equivalent from the density, it will work fine. And you can add a little water bag, making up of 1 centimeter. But you have to be very careful with placing this. So I made some tests. So just by placing a water bag, you can cause some pressure onto your channels, which is especially if the water bag is over this material where you put have your catheters planted in. So so it might happen that when you do a measurement, you do not see almost any change, but you can place 1 centimeter.
Okay, thank you very much, ma'am, for sharing your knowledge and giving your valuable time to us. And I would like to thank to Chairman of SCM-PCR, Professor Dr. Ghulam Abu Zakaria sir and Professor Dr. Asin Anupama Hajari ma'am to giving this opportunity to me. And thank you very much all participants once again. We appreciate your presence here. Our next lecture is on 12 Feb 2021. Please save your time and date. Thank you everyone.
Thank you. Goodbye.